Good day, my dear students. Let's continue with some more problems on mathematical induction in combinatorics from where we left last time. And so there is an exercise which is a nice exercise, exercise 1 of the day. Use mathematical induction, to show that h 2 raised to n is always written equal to 1 plus n by 2 for all n equal to 0, 1, 2 and so on, where h j is given by 1 plus half plus 1 by 3 plus so on 1 upon j, and this is for all j equal to natural numbers 1, 2, 3, etc. And this is called the harmonic numbers. Harmonic numbers are defined by h j. You can have h1, for instance. If you write h1 would be 1, h2 would be 1 plus 1 upon 2, h3 would be, so it's easy to see what is the harmonic number. So likewise you can define general hj. Now we have to show that this is what we have to show, that is our property. Our property that we need to prove using the mathematical induction, this is actually our property. And what do we do in mathematical induction proof? Well, the first thing is the basic step. The basic step, I have BS, but it's a basic step, that P of 1 is true. How do you know P of 1 is true? That means h 2 raised to 1, n equal to 1. This is true for all n. Oh, n equal to 0, that's the smallest one. N equal to 0, which is h1, which is 1. Is it greater than equal to? Is that greater than equal to this 1 plus n equal to 0? So 0 divided by 2, yes, it is. It's actually equal. It's greater than equal to. So that's actually equal. Second is, let pk be true. Pk be true. To show that pk plus 1 is true. Well, every time we use the same thing. Mathematical induction is pretty simple. Sometimes you may have to adjust a little bit here and there. Well, pk is true means I told you what was pn. Pn just says that h 2 raised to n. What does pn say? That's greater than equal to 1 plus n by 2. So pk should imply is true means h 2 raised to k is greater than equal to 1 plus n by 2. What are you supposed to show? You are supposed to show that h 2 raised to k plus 1 is greater than equal to 1 plus k plus 1 by 2. This is what I will show, but this is what you assume is true. Well, let's take that. What happens? I want to show this, but I'm going to use this. Well, what is h raised to 2k plus 1? Well, it's going to be 1 upon 2, 1 upon 3. You will have to come somewhere, last term will be plus 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 1 upon this number 2 raised to k plus 1. Well, that's actually equal to 1 plus 1 upon 2 plus 1 upon 3 plus somewhere you will get 1 upon 2 raised to k before that. And plus this goes up to 1 upon 2 times this thing can be written as 2 raised to k. I hope you can see what is happening there. Right? But that can be written as 1 plus 1 upon 2 plus 1 upon 3. Up to this place is my hk. Hk. But that's alright. 1 upon 2 raised to k. This is hk. Plus, what is the next term? 1 upon 2 raised to k plus 1. Plus 1 down, not on top. Plus 1 upon 2 raised to k plus 1. Plus 2. Plus 1 upon, it's 2 times that is 2 raised to k plus 2 raised to k. I hope that's clear. I hope that's clear. So what happens is this guy is hk. Let me write that. Pk is true. I think I wrote that statement. Pk is true means h 2 raised to k is greater than equal to 1 plus. I wrote n by 2. It's k by 2. Please correct that. I think I wrote n by 2. This is what we have assumed. This is what we want to prove. I have taken the left hand side. And eventually I want to show that that's what I'm going to use this. This is every time, this is the way we go on. So, my pk, as I said, I had written it wrongly, I think. My pk is that h 2 raised to k is greater than equal to 1 plus k by 2. It's not n by 2. By mistake, I think I had written n by 2. Please correct that. But this is hk. So I'm now going from here. This is hk, h2 raised to k, not hk, h2 raised to k. Plus, you see, I have those many terms there. So, how many terms are there? These are 1, 2, so on. So many terms. I could actually write that as, tell you, I can actually write that as, so I can actually put here, so 1 upon, so this will be greater than equal to, in fact greater than, strictly greater than 2 raised to k plus 2 raised to, so 1 I am replacing by 2 raised to k, 2 I am replacing by 2 raised to k. And so on, plus. The last one is also 2 raised to k plus 2 raised to k. And 2 raised to k, you see, is going to be bigger than, because this 1, 2 increases up to 2 raised to k. So 2 raised to k is bigger than all the previous guys. So I am writing a bigger term down in the denominator, and therefore this is going to be h 2 raised to k. This is actually, you see, it's 1, 2 raised to k. So there are plus 2 raised to k times 1 upon 2 times 2 raised to k guys. Each one of them is 2 times 2 raised to k. Right? Yeah, of course, right. So what do you get? So you started with h 2 raised to k plus 1, you get this expression, greater than equal to that. And now what you get is, you see this h 2 raised to k, I am assumed to be true, will be greater than equal to 1 plus k by 2, and this becomes 1 upon 2, and the whole thing becomes 1 plus k plus 1 by 2. And that's exactly what is the right hand side that we have to show here. Therefore, this is the right hand side, and everywhere it is greater than equal to, somewhere it may be strictly greater than, it doesn't matter. So the result is true. Good. is true. Let me solve a few more on induction because this is an interesting one. This is a very interesting one. Next one is very interesting. Requires a little more thinking. Sometimes you got to do some adjustments so that in the and the basic step was P0. It was not P1. I think sometimes I wrote P1, but actually the basic step here was P0 because it was h 2 raised to 0 and h 2 raised to n. This is the property that is equal to 1 plus n divided by 2. This is the property that we have to prove for all n equal to 0, 1, 2 and so on. The basic step should be the smallest one. So this should be P0, not P1. I think I wrote that P1. Please correct that. That's one thing. And this is actually J is defined as 1 plus 1 upon 2 plus 2 1 upon J. If it is H10, it will be 1 plus 1 upon 2 plus 1 upon 3 up to plus 1 upon 10. That's the definition. So this is going to be H1. Therefore, it's going to be only 1. Is that greater than or equal to 1 plus n by 2? But n is 0, so it is 0 by 2, and the answer was yes. So P0 was right. Pk was assumed to be true. This implies Pk plus 1. We have already proved. The result is done. But the next problem is interesting. So please correct that. I think I might have written P1 here. And when I wrote Pk, I think initially when I wrote Pk, I wrote that h 2 raised to k greater than or equal to 1 plus n by 2. It's not n, but it's k. I think I made that mistake. Please correct it. And then, okay. Okay. The next one is very useful, very neat example. Use mathematical induction, right? Short form. MI stands for mathematical induction. To show that if number of elements in a set, sometimes written like this, cardinality of, this also means number in an element. S is n, say n equal to 0, 1, 2, number of elements could be 0 as well. Then what can you say? Then the number of elements in the power set of S. What is the power set? Is 2 raised to n. What is the power set? This is the power set. What is the meaning of power set? So suppose if I take a set like having 1 and 2 elements, what is the power set of A? Is set of all subsets. First of all, every set is a subset of this. A is a subset of this. 1 is a subset of that. 2 is a subset of that. And it has 2 raised to 4 elements. So here there are 2 elements. And 2 raised to 2 elements. So 2 raised to 2, that's 4 elements. Number of elements here is, if there are n equal to 2, this is 2 raised to n. Okay. So suppose B has elements, say 1, 2, 3. Then power set of B, you can write all sets, including the empty set and the whole set and all other subsets. Empty set included, number of elements. So this, I'm not writing this, please write it. You see number of elements here is 3 and therefore you expect number of elements here to be 2 raised to 3. So how do we prove that? Proof is very nice using mathematical induction. It's very nice, neat proof. And so the first basic step is P0. Sometimes I write by mistake P1, but the first step need not be P1. It's P0 here. Sometimes it could be P5 because it may not be true for the first few values. So it depends. See, solution. Proof. P0 true? Is P0 true? That means if you have a set which is empty set, that means number of elements in S is 0. So number of elements in S is 0, n is 0. Then what is the power set of S? What is the power set of S? Power set is set of all subsets of S. And the only subset it can have is the empty set. So number of elements in power set of S, can I say is 2 raised to 0, which is 1? And obviously it is 1. There is only one element. Think of it. Think of it. This is an empty set. Power set means all subsets of this. Put all subsets of it. How many subsets are there of S? Only the empty set is inside an empty set. Only the empty set is inside an empty set. Nothing else. So this is true. That's the basic step. Basic step. I just write short forms. Induction step. Let Pk be true. What does this mean? If S, number of elements in S is K, then this implies that number of elements in power set of S is 2 raised to K. That's what it means. Let Pk be true. Let Pk be true. To show that P of K plus 1 is true. What does that mean? P of K plus 1 is true. P of 0 is true. That is the basic step. The first value of n. That's true. I hope you can confirm and you can convince yourself. Assume Pk is true, which means that if a set has k elements, then the number of elements in the power set is all subsets, should have 2 raised to k. If you assume this is true, you should be able to show this is true. What is Pk plus 1? Well, what does Pk plus 1 say? Pk plus 1 says, so Pk plus 1 here implies and implies back. If you want to show this, you will have to show that if number of elements in S is K plus 1, this should imply, number of elements in power set of S must be 2 raised to K plus 1. How do we do that? This is a nice idea. This is a nice idea the way it's proved. So S says K plus 1 elements. So S is a set like you have x1, x2, xk and xk plus 1. Remove one of the elements from there. Any one element. Maybe we remove the last one. Any element. So remove an element. Call this new set as X. Remove an element, maybe first one, maybe last one, I don't care which one. Just remove one of the elements. Now this X will have elements like x1, x2, xk. So number of elements in X is going to be k. And by our assumption, Pk is true. Therefore, number of elements in the power set of X must have 2 raised to k elements. Good. I am using the assumption. Now, how do you go to so if you take a subset A, if A is contained in X, for every A contained in X, and X is already in S because X is obtained from S by removing one element. So X is obviously a subset of X. Okay? So for every subset of X, there are 2 subsets of A. Of S. There are 2 subsets. This is one. The other one is A union. That element which is removed. This one also belongs to S. So for every, let me write this, for every subset A of X, there are exactly two subsets of S, that is A itself and A union the element that we have taken out. So corresponding to every subset of X, so it's like this. So you have you have X, and any subset of X, that means any A belonging to the power set of X, any subset of X, then you have S, then you have two corresponding A and A union the element, one element that you have taken, which belongs to power set of S. So every one element here, there are two elements here. What does it tell you? Therefore, number of elements in P of S must be double the number of elements here. 2 times number of elements in power set of X. I hope this is very clear to you. This is something that is little, I liked it, because you take an element, a subset of X, but X is already a subset of S, therefore A is also a subset of S, but there is another subset which comes along with this A, along with A is this one. And that covers all the subsets of S. That covers all the subsets of S. All the subsets of S. Think about it. So, number of elements here must be 2 times number of elements here, but then 2 multiplied by number of elements here by assumption. By assumption, we had proved that this is, we had assumed this is, so this is 2 raised to k plus 1, and that completes our result. Please look at it very carefully, but this is a beautiful proof. It's a nice idea, and once you understand, you feel really good. So, and it's not difficult. It's exactly for every element that are exactly 2. For every subset of X, there are 2 subsets of S, and they give all the subsets of S. If you take all the subsets of X, you get all the subsets of good S. So let me say that again. You have X, which has, you are given S, some k elements, x1, xk plus 1, k plus 1 element, xk is here. You write minus, remove one of them, maybe the last one, and therefore this set has only k elements. And then if you make a subset here, and this is already in S, you get 2 subsets A and A union the last element which you have taken. And these are subsets of S. These are subsets of S. They are contained in S. And the point is, if you cover all the elements in P of X, if you take all the elements, you get all the elements in P of S. If you take all the elements here and then you take all these elements, they give all the elements of P of S. And that is the crux of the matter. Good. Let me do a few more. This is another nice example. It's called the odd pi fights. Odd pi fights. An odd number of people stand. So odd number. People stand in a yard mutually distinct distances, if each person throws a pie on the person nearest to him or her, and if all of them do this simultaneously, and if all of them do this simultaneously at one time, then show that there is at least one person who is not hit by a pie. Then show that there is at least one person who is not hit by the pie. Good. What does the problem actually say? An odd number, so it could be 1, 3, 5, 7, and so on. An odd number, no even multiple numbers. Mutually distinct distances. That means if suppose fellows are standing somewhere, one of them may be closest, two of them may be closest, A and B might be very close. So this distance may be 1, this distance cannot be 1, something else, maybe 3. This distance cannot be 1 and 3, maybe 5. This distance cannot be 1. So they all got to be different distances. They all got to be different distances. Like this distance might be 4 because it's not there. This distance may be 6, it's not there. This distance may be, I don't know, 5.2. Distances are distinct. They are not the same. This distance might be whatever, 6.5. But the distances are distinct. Good. If you think of this problem, it looks like a very complicated problem, but when you use mathematical induction, it becomes very easy. So the problem says, odd number of people standing mutually distinct distances, that means any two distances between any two people is different. Distinct distances, different distances. Different. Any two distances are different. And you throw, so if two people are very close and the others are far from them, they have to throw only on each other. They have to throw only on each other. You throw on the closest person. You don't throw on the fellow. That's the rule of the game. So, if each person throws a pie on the person nearest to him or her, and if all of them do this together, then show that there is at least one person who is not hit by a pie. Good. So the basic step should be, you understood the problem now. The basic step is, you have odd numbers. You have 1, you have 3, you have 5, you have 7, you have 9, 11, and so on. You have odd numbers. Therefore, you must have something like 2n plus 1 or minus 1. If you put plus 1, then it takes values like n equal to 0, 1, 2, 3, and so on. Now it takes 2 because it's going to give you 5. So, first property P is P0 true. P0 means you will have only one person. And nobody throws a pie on himself, so it's vacuously true. Clearly true, vacuously. We say vacuously true. Because there is only one person. There is only one person, so it is vacuously true. Suppose you take P equal to 1. I'm not taking 0 persons, I'm taking 1 person, so it comes this. When you take P1, it means there are 3 persons. Because I'm taking this formula. This is Pn. So, if you have 3 persons, so you have A, you have B, you have C. Suppose these two guys are the closest. I mean, among the 3 people, all 3 can't be close because the distances are different. Even the distance from here to here should not be the same. So maybe something like this. So if this is 2, this is 5, then this must be 7 or something like that. So suppose this is the distance. There are 3 people. Then let say there are 3 people, A, B, and C. Let A and B assume A and B are the closest. Then A throws on B and B throws on. So then A and B throw a pie on each other. They will throw on each other because they are the closest. So A throws on B because B is the closest. B throws on A because A is the closest. C has a choice now because this is 7 and that is 5. C will throw on B. C doesn't have a choice. Sorry. C doesn't have a choice, but if this is the condition, C has to throw on B. But the point is nobody is throwing on C. C is not hit by a pie. C is not hit by a pie. So there is somebody who is not hit. When there is one person, it's true because whoever that one person is, say Mr. X or A, suppose A is there alone, A is not hit. A is not hit. So P0 is true, P1 is true. It was enough for me, basic step was enough for me to say P0 is true. Was enough. Now let's go to what do we go? Where do we go? Now let's go to the inductive step. So the basic step is true. I don't have to say this, but it's alright because it's a nice argument. So what is the inductive step say? Inductive step, so this is the basic step. The inductive step says let Pk be true to show that P of k plus 1 is true. What does Pk mean? Pk is true. That means of 2k plus 1 people, there is at least one person not hit by the pie. To show that of 2k plus 3, because when I put k plus 1 it becomes 2k plus 3. Of 2k plus 3 people, there is at least one person not hit by a pie. Not hit by a pie. So I assume this, I got to prove that. Good. Now look at the argument. These are not my arguments, these are some sort of problems. And they are nicely, nice arguments, nice reasoning. So I assume Pk is true. I assume now there are 2k plus 3 people. two persons from 2k plus 3 people. So if they are the closest, because you have so many people there will be two people who are the closest. There will be two people who will be the closest. Imagine like you are standing on a line and the distances are not the same. So one fellow is here, next fellow is somewhere far, third fellow may be very close, fourth fellow may be somewhat little, but the distances are not the same. So and they are not on a line, they may be jumbled up, but still the distances, mutual distances are different. But there will be some closest guys, whether here or here, there will be some closest guys. And that's without any doubt. So if A and B are the closest, then A and B will throw a pie on each other. There is no doubt about that. And A and B will throw a pie on each other. Now there are two conditions that can take place. Case one. There are two cases that can crop up. The two cases that can crop up are like this. Two fellows are close and all the other guys are very far. Now they throw on each other. This guy is not going to throw on him because these other guys are closer to him. He will choose on the closest guy or near him. He will choose the closest guy near him. He did not throw on him because there will be somebody who is closer to him, to this guy, so he might throw on him, and so on. This guy may throw back here because there is nobody close. I hope you understand. So case one is nobody else throws a pie because A and B are far. They are close to each other, but they are far from the remaining of the group, quite far, and therefore they throw on each other and nobody else is throwing on them. Right? Nobody else is throwing on them. And nobody else throws a pie on A and B. Okay? They throw on each other, but nobody else throws on A and B. This remaining group, because there are two here, and total group had 2k plus 3, this remaining group will have 2k plus 1. Because this plus this together must be 2k plus 3. Well, because this group is 2k plus 1, it satisfies pk. Therefore, the remaining group of 2k plus 1 persons must contain at least one person who is not hit by a pie. So I made use of the assumption because nobody else from here is throwing here. They are throwing among themselves, but this group is smaller, so there must be one guy at least by assumption. Good. Second case is, so this is one case. The second case is case 2. Second case is A and B are throwing on themselves, but there is somebody else because it so can happen that there is a guy here and then the guys are far away here. These guys throw on each other, A and B. A and B throw on each other, but there is a C who's far away from the remaining group. So there are two guys here, there is one guy here, and there is a group of altogether 2k plus 3. So there is a group of 2k. There is a group of 2k. It so happens that A and B throw on each other, and so there is at least one more person who throws a pie on A or B. So C might throw on A if A is closed, or B because B is closed. There could be even another fellow D here. There could be another fellow D here who also finds B is closed. This one finds A is closed. At least one. Then in which case there will be 2k minus 1. Good. So if there is at least one more person who throws on A and B a pie, right? So two pies are already here because A throws a pie, B throws a pie, and then C throws a pie. So there is at least one more. There may be two more pies. There may be three more pies. I don't care. There is at least one more. Then remaining group here, including the C and D and everything, has 2k plus 1 people. And if one and the pies, number of pies will be less than equal to 2k, because at least one is going there. Each one of them got a pie, so at least one of them is throwing there. That means now these are 2k. Two people are gone, so this is 2k plus 1 people. All of them together. All this together is 2k plus 1 people, because this 2 is here. 2 people are here. 2k plus 1 is here. At least one of them throws a pie. We have considered first that none of them throw a pie here. That case is over. At least one of them throws a pie. There were already 2 pies here, and you are throwing one more or 2 more. So there will contain 2 plus 1 or 2 plus 3 or 2 plus whatever. There are more than 2 pies there. There are less than 2k pies here. Total number of people are 2k plus 1. Total number of pies is less than or equal to 2k. Total number of people here are 2k plus 1. At least one of them must not be hit by a pie. Therefore, so you can see that A and B will be hit totally by at least 3 pies, and the remaining 2k plus 1 persons will be hit by at most 2k, because 3 are gone or 4 are gone, at most 2k pies. Therefore clearly, when 2k plus 1 people are there and 2k pies are there, maximum 2k pies are there. Suppose even 2k pies are there, you can't hit 2k plus 1 people. At least one person. Therefore, at least one person is not hit by a pie. And that completes our beautiful proof of this statement. So if you have odd number of people whose distances are mutually distinct, not the same, no two distances are the same, each one of them throws a pie on the closest person, then at least one person is not hit by a pie. Maybe I should solve one more problem before I call it a day, because these problems in induction are very nice. I'm sure you will like them as much as I do. Okay, here are some more problems I have taken. I am taking problems from this book. I forgot to mention to you that I am taking problems from the book Discrete Mathematics and Applications by Kenneth Rosen. Very nicely explained and nice problems. Problems are clearly explained, so you feel comfortable with it. Alright, let me let me do one more problem. Which you may like. I mean, these problems are nice once you get the idea clearly. They're pretty simple. I don't remember the number of the exercise. I don't know what was the number of the exercise, but I saw whatever 3 maybe of the day, 3 or 4. Let n belong to n be a natural number and m plus 1, m plus 2, up to m plus n be n consecutive integers, then show that exactly one of the n integers is divisible by n. Oh, what does it say? Well, let's understand the statement. Or I could write it like this instead of that. Let n given to n, then show that same problem. Let me rephrase it. Show that any set of n consecutive integers, any set of n consecutive integers, then show that in any set of n consecutive integers there is exactly one divisible by n. So I hope that statement is clear, and the problem is very simple. So what it says is, maybe you take this as a problem or this as a problem, whichever statement you like. It says that if n is a natural number, suppose you take 5 is a number, natural number, and you take 5 numbers from variable -1, 0, 1, 2, 3. These are 5 consecutive integers. 5 consecutive, that is one of them is divisible. Exactly one of them, not at least one of them. Exactly one of them is divisible. Not more than one, exactly one. Suppose you take numbers like, not only these 5 numbers, suppose you take numbers like, say, 3, 4, okay, suppose you take numbers like 6, 7, 8, 9, 10. 10 comes there, 10 is divisible. So you know, I mean, exactly 1, the rest are not divisible. Here exactly 0 is divisible, here exactly 10 is divisible, no other number. So, for instance, if you take say 10, oh, why take 10? Let's take some 11. And you take 11 consecutive numbers, say -4, -3, -2, but 0 comes there, so 0 obviously. Let me take something like, you can take, what I'm trying to tell you is, Suppose you take 13, 14, 15, 16, 17, 18, 19. You take 11 numbers which are consecutive. 20, 21, 22. How much you want? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you see 22 is the only number that's divisible by 11. Exactly 1. Is the only. There is one and only one. So that's what he's trying to say. So let me solve that using, how do we solve it? Do we use mathematical induction here? I think this uses something known as the next principle that I want to do, but I want to solve some more problem. The next one is, I think, pigeonhole principle. I think this is solvable by pigeonhole principle. Let's do it again. So you have m plus 1, you have m plus 2 solution. You have m plus 3. I am not actually doing it by induction, I am doing it by pigeonhole principle, which I have not actually said what is the pigeonhole principle. That is the next. I think I took a wrong problem. Anyway, but let me solve it. This I am supposed to solve in the next. So these are n numbers, consecutive numbers, n consecutive, because m is an integer. These are integers. M belongs to z. N belongs to n. Okay. So m plus n has to belong to z. There is no doubt. So all these numbers have to belong. Okay. Now this can be written as n times some quotient plus remainder. To divide by n, this can be divided by n times some remainder. This can be divided n times q3 plus remainder. You know the division algorithm. And this can be written n times q n plus rn. And each of these remainders Ri must be greater than or equal to 0, less than n. You see, for all I equal to 1, 2 up to n, there are remainders. There are remainders, the values it can take. And if I want to say that these Ri's are all distinct, first claim, I am not using mathematical induction here. Anyway, but this is a nice problem. I will probably do it again when we do pigeonhole principle. In fact, we use that principle here, which says that if there are 5 holes and there are 6 pigeons, then 2 of them must go in the same pigeonhole. Somewhere 2 must go. If you have 7, one of the holes will have, at least one of the holes will have 2. Anyway, so pigeonhole principle is a very simple principle. I have not stated, but I am going to use it here. Claim is Ri's are distinct. That's the first claim I want to prove. Ri's are distinct. They are not the same. Ri's are distinct. They are different. Suppose Ri is equal to Rj, one of these, for some 1 less than equal to I less than equal to j, less than j not equal, and less than equal to n. There are n Ri's. Suppose this happens, then what happens is m plus I is equal to n times qi plus ri. M plus j is equal to n times qj plus rj. This is what we are saying. If you subtract, you get j minus I will be equal to n times qj minus qi, and which means n divides j minus I. And you know, because these two are less than n, j minus I will be greater than equal to 1, but strictly less than n, and n divides a number which is smaller than that. This is a contradiction. Why did this contradiction come up? Because I made a wrong assumption that I am saying Ri's are distinct, but I am saying suppose two of them are same, they can't be same. Therefore, this claim is true. These numbers, remainders, all are distinct. These remainders are all distinct. Okay? So they can't be equal. No two of them can be equal, so therefore no three of them can be equal. And you know why the contradiction, because n divides this number will be smaller than n. And think about it. Just please apply your mind. Well, if that happens, now these Ri's are I equal to 1 to n. There are n of them. And I'm saying that, you know, these Ri's are less than n and greater than equal to 0. Suppose I say none of them is equal to 0, then these are n fellows. If none of them is equal to 0, then they must be, you know, either equal to 1, 2, and up to n minus 1. And this, if n fellows have to go here, it's a pigeonhole principle. Pigeonhole principle says that if there are, suppose, n holes and n plus 1 pigeons, then at least 2 must go somewhere. So I have n remainders and I say none of them is 0, then 2 of the remainders must take the same value, which contradicts this, that they can't be equal. 2 of the remainders must take the same value, means those 2 remainders will be equal, which gives a contradiction. So I'm using the pigeonhole principle, which I will state in the next chapter. But if R is not equal to 0, if no Ri, if Ri is not equal to 0 for all I equal to 1, 2, n, then we have a problem, because we have n remainders. They have to take n minus 1 values. 2 of them will have the same value, 2 of them cannot have the same value. Therefore, one of them must be, therefore, please write, therefore, exactly one of the remainders must be 0. Please apply your mind. Exactly one of them must be 0. What it says is, therefore, if you have n consecutive integers, then n will divide exactly one of them. I like to stop there. Thank you so much. I like to stop here. If you have any doubts, please write to me.